Okay, next speaker is Dr. Selma. She is a postdoctoral scholar with the Department of Computer Science at Stanford University. Through display, but I'm happy to see you again. So if you are ready, can you share your slide?
Thank you. Happy to see you.
Yeah.
Let me check quickly. Sorry for the delay. Okay. Do you see my slides?
Yes. Yes. Can you start
Okay.
slideshow, maybe?
Yeah, let me just. Yep. Okay.
Okay, let's start.
Thank you. Hello, everyone. My name is Selma. I'm jointly appointed with Stanford University and Technical University of Munich. So I would like to talk to you about shared control for human multi-robot or human-robot team interaction. So we already heard a lot about HRI and human multi-robot interaction. So I would like to start this talk with reminding us about how we use multiple robots nowadays, specifically focusing on collaborative robots or cobots. So there has been a lot of work about humans and robots sharing workspace, but also one important question in modern HRI is how to share decision-making and task execution. So if we imagine a scenario where we have multiple humans and multiple robots performing a complex task with multiple aspects of the task being executed at the same time, challenge is really how to resolve the increased complexity, complexity in terms of robot systems that we have, task interaction, but also complex environments that we see nowadays. So in this sense, I focused my research so far on what I called human-robot team interaction, but in this context of the topic, of course, it's pretty clear. For me, it is interaction between single human operator and multiple cooperating robots, and trying to resolve these challenges in such a scenario where I have multiple degrees of freedom of the robots and a single human trying to interact successfully with such system. So the question here is how to design control. For me, the question is how to design appropriate control for shared task execution, hopefully on a higher level decision-making in such complex settings. So in terms of shared control, of course, it's a very broad concept that relies, of course, on semi-autonomy of robots, but in the context of human-robot team interaction, we have sort of sliding scale concept from what we know when human is fully in control, like classical teleoperation, for example, when human controls all degrees of freedom, and of course, full autonomy that is still very difficult to reach. So everything in between for me is shared control. And in this sense, I want to exploit it to complement capabilities of humans and robots. Of course, cognition on one side, humans are still much better at pre-planning and higher level kind of understanding of the world around us, and robots are very good at precision tasks, but also for tasks that reduce human workload and assist, especially in teleoperation and inaccessible and dangerous environments. So we have a control strategy between human and robot, and we want to design this shared control. And in this context, of course, human is planned to be in the loop. There are, of course, a lot of strategies, and we heard today that maybe human is providing some high-level command or has supervisory control. But in this context, for me, it was really human in the loop with the robots and seeing how these tasks can be performed. And of course, robot expecting to have this sliding scale of semi-autonomy, depending how much is necessary for a specific task. So really, in this context, commands of the human operator and robot autonomy would need to be combined in some way to achieve a task. In this sense, when we have, for example, teleoperation scenarios, but maybe direct physical interaction, really the question, of course, is interface. And we've seen some really cool stuff today about how to guide many robots and swarms effectively. But for me, of course, because I am focused on physical tasks, interface that is essential in this sense is haptics, and all sorts of haptic devices are now available. And what I wanted was to exploit this these channels to provide adequate motion and force signals both ways. So in this sense, we have many haptic devices that are either like robots or are wearable. So for me, pretty interesting were wearable robots and how wearable haptics and how I can exploit those in such scenarios. So basically, these were the focus. And as I said, haptic channel is really essential for any type of tasks that require interaction with the environment, which was pretty interesting, for me. And then we come to the concept of haptic shared control that can be utilized in human multi-robot systems in all sorts of ways. For example, in telesurgery, swarm control, collaborative manufacturing, and many other examples. There are, in this context, in this introduction, there are multiple challenges that are relevant. And one interesting is really how to design, as I said, this interaction that is independent of the setting, interface, and robot structure, which would maybe mean that we want to transition from some remote interaction to direct physical interaction in one big task. In this sense, another challenge that was interesting for me, how to simultaneously then perform these multiple control objectives effectively that arise from such a complex task. And of course, if we have interfaces that are required in such settings, haptic interfaces, how do we design adequate command and feedback channels from human to robots and vice versa? Of course, for me, it was utilizing wearable haptic interfaces and then effectively understanding what sort of signals we can send to human that would be understandable and effective. Another two challenges are, of course, higher level challenges, how to model this human in the loop for effective decision making and how to design such controllers. So really the objective would be to design this control framework for focusing on continuous haptic aspect of human multi-robot or human robot team interaction. So in this talk, my focus would be on these highlighted three challenges, meaning designing particular controller and then seeing how wearable haptics and these command and feedback channel designs can be done. So first part is really control focused, and then the second part is utilizing it on an example. So really starting from the idea that we have a human that has relatively low dimensional channel compared to the system we want to interact with that has many degrees of freedom. And we have a task that has its multiple aspects, and robots can be, of course, heterogeneous, as you've seen on the first photo, maybe on one of the first slides. They can have, of course, mobile platforms, manipulators, and so on. And really what we have here is certain asymmetry that needs to be resolved. So starting from the task that for me represents in this control sense, set of control goals and constraints on my environment and the system and even human. So this is the formal definition of a task for me. I assume to have a library of behaviors that robots can have in this collective. And retrieving these behaviors whose successful execution in a combination would give me task. What I have is a set of subtasks that can be interleaved. And for me, these subtasks represent individual control objectives that need to be achieved. So by allocating these subtasks, for some human is responsible and for some robot team autonomy is responsible, I would have this concept of shared control achieved. So in that sense, I developed subtask-based shared control approach throughout my research. And the intuition for this allocation, of course, it's an interesting question, but of course, knowing intuitively how to do it is like some high-level tasks that are really goal-oriented. These can be really responsibility of human, and some lower level tasks can be responsibility of robot autonomy. So in this sense, an example that I analyzed is the one of cooperative object manipulation, where I would, for example, have naturally arising subtask of, I need to grasp the object with multiple robots and maintain this grasp while performing object manipulation or transporting task that human can guide this collective towards a goal, for example. So moving from individual degrees of freedom of such a system towards a bit of higher level of abstraction, I want to achieve control on this level, of course, which has been done in many ways so far, but in the context of wearable haptics, it's pretty interesting to perform such scenarios. So really, we can start from a model of this complex system, but the idea is having a representation of a model. We are designing a shared control that would combine effectively control input of the human and control input of the robot, while we have some effects from the environment. We want to design this controller to have certain behaviors, which would be connected to outputs on the next slide. So really starting from, for example, Euler-Lagrangian dynamics, and by stacking it, we have this representation of our dynamics. Effectively, behaviors, by defining behaviors, there's certain these abstract states. We can perform mapping of this complex system, project mapping to lower dimensional space. And these mappings are actually constraints. And I dealt here with equality constraints, but of course, inequality constraints are also possible. And these can be really constraints that are determined by environment that are natural, like if this system needs to grasp the object, that is actually a natural constraint on the system, or artificial. For example, we have certain swarm shape of multiple UAVs. So by having these abstract states as constraints, I can have them as my outputs, and what I need to do is design effective input-output behavior to have my subtasks achieved. So this is the idea that by having these behaviors as outputs and then having control goals, certain control goals assigned to these outputs, I achieve my subtasks. So of course, then a differential map of this would be determined by certain Jacobian, and certain properties need to be satisfied for such outputs to be valid. But essentially what I want to have is representation of my dynamics on a higher level. And then I would have multiple dynamic subsystems that I want to control, and that would describe my dynamics. So this behavior dynamics then starts from the original system and is determined by these behaviors. So how to actually design this? The idea is on a simple task that we want to have on this level of behaviors that certain dynamical representation of behavior is controlled by the human partner. So for example, first dynamics and its output controlled by the human partner, and the other one controlled by the robot partner, as in the example of cooperative manipulation. We want robot autonomy to control grasp maintenance and human to control motion of such a complex system. And of course, in this case, we don't want these to interact, for example, through haptics. So we would need certain decoupling control to ensure that there is no interference, and then control on these level of behaviors with some nominal control actually to achieve desired subtasks. So in order to design this decoupling control without going into a lot of details, we want to have input-output control so that control input of the human affects only the behavior or the output assigned to the human, and robot autonomy controls only the system and the output, the other system and the other output. So in this sense, we want to have this controller, and on top of it, we want, because of this whole level of physical interaction, certain safety guarantees that can be loosely speaking, ensured with passivity-based control, so this nominal control can be passivity-based. In that sense, decoupling control can be designed in input-output sense, so that on this higher level, formally speaking, what we have is that this matrix that connects control inputs to the dynamics. This input matrix is really block diagonal, so there are no interactions between these dynamics through control inputs. If we want, but this is, of course, it really depends on the design of the system, that other components of the dynamics are non-interacting so that we can achieve full non-interaction. Then, of course, we can design control so that our Coriolis terms are non-interacting as well. No, of course, assuming we know dynamics full well, but it is really not necessary for input-output control to be achieved. In that sense, we could theoretically have these control, system, so to say, abstract systems fully decoupled. And then, for example, in the context of cooperative manipulation, impedance control, designing impedance control for each subtask can ensure passivity guarantees, and is really convenient as this nominal controller for such interactive behaviors. So applying this to a teleoperation scenario, we want to have something like on this video. Of course, we've seen examples of this. We want to have it as a formation or with cooperative manipulation, but to be able to control this whole system, and not as in classical cooperation to directly control degrees of freedom of the system, which is often done. So in this sense, basically, this is the goal, to have such a behavior between manipulators, for example. For this, because we have this asymmetry, to remind to one of the motivational slides, we have many degrees of freedom on one side, and then our shared controller, plus we can use wearable haptics on the human side to get information from multi-contact points of the robots interacting with the object. So wearable haptics are really nice for this because we can get information of what is happening to manipulators, for example, or what is happening to individual robots if necessary. Talking about decoupling control, what can happen if we have wearable haptic devices, we really need to ensure this decoupling, because if we have some of these interactions between subtasks, they can really be sent through haptics as disturbances. And then this can really complicate interaction of the human with the system, because these disturbances, as human doesn't control one subtask, would be really difficult would really be difficult to get resolved, and could lead to instability, as we'll see. So these coupling effects between subtasks can be a problem and a disturbance through the interface, which is why we would need such a decoupling controller. Applying these concepts of behavior, of course, the cooperative manipulation is intuitive for this, which is why I use this example. But like I call this relative behavior between robots, which basically ensures our object to be grasped, and can be defined as equality constraints, of course, by defining distances and relative orientations between each robot, which is really like sort of defining formation control between robots. And applying to such a behavior impedance control, as we'll see, really ensures our kind of internal behavior on the object level to be ensured. And cooperative behavior is nothing but applying grasp matrix equality constraints. So this is really not new and used from the literature, but is really adequate in the context of this entire framework. In this, by designing sort of formation, this relative behavior like a formation, combined with this concept of grasp matrix in the context of subtask-based shared control, what we have is really physically meaningful behaviors that are decoupled on an input-output level, because they already lie, one already lies in the null space of the other, which is the requirement for decoupling. So applying these Jacobians of such relative and cooperative behaviors, we can get cooperative and relative dynamics, which is not fully decoupled in the sense of state, but in the sense of inertia matrices or input-output sense. And then really we can achieve this decoupling for this specific task with certain parametrization of Jacobian matrices, and then control these dynamics separately. And then haptic feedback is also meaningful, like what we measure on the object side. And decoupling this is also meaningful in the sense that one provides inertia information and the other provides information about internal forces. So without decoupling, this is a simple example done at Stanford. What we have without decoupling is that because of these coupling effects through haptic device here, the object wouldn't be able to be lifted. The video is actually of the successful task, but the object wouldn't be able to be lifted and excessive grasp force would be commanded on the object. But in the case with decoupling, we can lift the object and move it around while the internal force is kept autonomously with certain algorithms. So decoupling control ensures safe interaction, including wearable haptics. I won't go into details because I see I'm close to the end. Including these devices into the control loop is intuitive, but of course we have seen that the information that we can send to these devices, of course, are very limited, and that we can get beneficial information if we send, for example, information only about internal forces. Without information, we can't have an idea about inertia of the object, for example, through such devices. So internal forces are useful information. So just to show a couple of videos towards the end, that guiding, if the human controls this cooperative behavior, the two robot manipulators autonomously perform this relative behavior, it is possible to of course, move the object around. And of course, this transition from no contact to contact is stable, and then in manipulation phase, there are no relative behavior, no relative velocities exhibited, which shows decoupling. And then it's possible to include more degrees of freedom in the system with mobile manipulators and multiple robots. With mobile platforms and multiple manipulators. So to conclude the idea of how to control multi-robot system in this way, using subtask concept is introduced, and the idea of using wearable haptic devices as multi-contact feedback. And of course, interesting would be to really allocate autonomously subtasks in some other scenarios, and to really understand human behavior and go a level higher to understand decision making and bit higher level controllers. Yeah, thank you very much, and I'd be happy to answer questions if we have time.
Thanks so much. Do you have any comments or questions? Okay, can I ask one question?
Sure.
I think you have a proportional theorem to keep dynamics passive. Why do you want to keep the dynamics passive? Do you close the loop by negative feedback for stability or other objective?
So the idea is for it to be, if we would, for example, yes, if we would have some, with wearable haptic devices, it's not so relevant really, but if we would have such a classical haptic device as was shown on a video, it is important if we would close, because we're closing the loop on one subtask to ensure it's passive. If we would include, for example, delays, consider delays. This is the idea, but also in the sense of just guaranteeing limited sort of energy, in the sense of no contact to contact, rasping the object. And for example, in the case of slips and these problems that can happen in the interaction with the object, we would just want to have this between motion and force, to have this limited sort of relationship.
Okay, so there are many uncertainty, but you want to keep the robot stable enough.
Yeah.
Oh, okay. Thank you so much. Okay, we have to move to. Okay, thanks so much again.
Thank you very much.